The Kumakivi balancing rock in Finland is a 280 metric ton mass of granite resting on a contact surface area of less than 0.24 square meters. Its effective center of mass sits exactly within 0.012 meters of the geometric instability boundary. Applying the standard Newtonian compressive stress formula, dividing weight by contact area, the rock generates a constant stress of 11.46 megapascals at that single fulcrum. Yet gravimeter readings taken directly beneath the pivot point reveal a localized gravity gradient deficiency of -12 microgals. Under classical geomechanical modeling, these gravimetric and structural variables do not reach an equilibrium state. The rock's continued stability remains outside the predictive range of standard Newtonian physics. Formations like this are known as precariously balanced rocks, or PBRs. Geologists use them as long-term negative evidence natural seismometers because their very survival places a hard upper bound limit on the maximum peak ground acceleration a region has historically experienced. This seismogram data charts seismic wave amplitudes. Mechanical engineering models predict that these specific microfulcrum structures must collapse during peak ground acceleration events exceeding 0.2 g. When we cross-reference this structural fragility with regional tectonic records, we find that the regions hosting these PBRs have endured multiple earthquakes with magnitudes of 6.5 or higher. The rocks should have suffered catastrophic failure during these events. Instead, they remain physically intact on the landscape. This means the probabilistic national seismic hazard models we rely on to understand fault zones are mathematically incompatible with the physical existence of these megaliths. The Naslaa sandstone formation in Saudi Arabia presents a different structural anomaly, a 9.3-meter continuous vertical split. The kerf width measures exactly 4.2 millimeters at the base, widening to 7.8 millimeters at the apex, maintaining a standard deviation of just 0.41 millimeters. The internal planar deviation is even tighter, remaining strictly under 0.8 millimeters over a 6.1-meter linear run. The classical uniformitarian explanation for a split like this is thermal weathering. If we calculate the maximum thermal stress generated by a desert diurnal cycle, a temperature swing of 42 degrees Celsius, the rock experiences a localized stress of 4.13 megapascals. We can compare that 4.13 megapascal force against the inherent properties of the Tama high silica sandstone, which has a tensile yield strength of 8.5 megapascals. The environmental thermal stress is less than half the force required to actually fracture the matrix. Thermal shock splitting cannot account for this cut. Scanning electron microscopy data reveals the internal split has a highly polished roughness index of 0.8 micrometers compared to the weathered exterior at 45 micrometers. Crucially, there is a complete absence of mechanical trauma, 0 microfracture propagation, 0 microflaking, and 0 impact microshatter. In 2023, isotopic dating of the iron oxide cementing layers established a minimum exposure age of 12,000 years before present for this exact split boundary. Standard subaerial erosion in this environment occurs at a rate of 0.02 millimeters per year. Based on that metric, an edge exposed to the elements for 12,000 years should be heavily rounded and severely degraded. Maintaining an edge radius tolerance of under 1.5 millimeters for over 100 centuries defies all known models of granular dissolution and chemical weathering. A different weight distribution anomaly exists in India, at the site of a formation known as Krishna's Butterball. Resting on a 45-degree slope with a tiny footprint, Newtonian mechanics dictate the gravitational pull should cause immediate downhill sliding, yet infrared thermography proves the rock exerts a continuous shear stress resistance that violates standard physics, maintaining a static friction coefficient greater than 0.85. To understand how this friction is physically possible, we look to 2016 piezoelectric excitation testing conducted on similar high silica sandstone and granite. These rocks contain aligned microcrystalline quartz networks, with silica concentrations exceeding 92.4%. Under the inverse piezoelectric effect, ambient seismic vibrations excite this quartz matrix. This generates localized electric fields and rapid microvibrations along the structural weakness planes. These exogenous acoustic or seismic frequencies alter the shear friction coefficients at the base. They create a localized fluidization effect that artificially anchors a mathematically unstable mass to the bedrock. We can apply this exact piezoelectric framework back to the Naslaa monolith, utilizing acoustic field resonance data recorded at the site in 1994. That 4.2 millimeter vertical slit separating the two halves acts as a precise geometric chamber, producing distinct standing wave reflections. A 2024 global survey mapped 8 precariously balanced rock sites, detecting persistent ultra-high-frequency acoustic hums between 1.4 and 3.8 Hz, locked in harmonic coupling with the strata. Superimposed 2025 quantum magnetometry data reveals intense microtesla magnetic anomalies localized within a 5-meter radius of these splits. The data suggests these formations function as active sites of continuous harmonic exchange, coupled directly to electromagnetic and acoustic signals of deep tectonic fault zones. We can cross-reference all of this gathered data with a 2026 global audit of destruction rates for precariously balanced rocks. The audit reached a definitive conclusion. Classical thermal weathering models overestimate vertical shear propagation rates by an order of magnitude. Current geomechanical models cannot account for the precise planar uniformity, the lack of edge degradation, and the seismic survival of these formations. There is no known historical or natural mechanism capable of creating a 9.3-meter continuous planar cut through dense quartz silica. The mechanics behind these precision splits and anomalous balancing remain unresolved. In these specific instances, current models of geology and geomechanics completely fail to account for the forensic evidence.